In this lesson, we're going to look at Newton's law of universal gravitation. Here's the equation you'll see right here. Okay, so for much of human time, they really didn't understand the universe, looked at Earth and thought, the Earth and the universe follow different rules. But then came along Newton, and you have heard of the apple story. And Newton's, whether it's apple or not, it doesn't really matter. But Newton noticed that apples and things that fell went straight down to the ground, and they were attracted to the earth. They were falling to the earth. And he started thinking about why an apple fell, but he didn't just stick to thinking about the earth. He started looking out there and wondering, why does the moon follow its pattern across the sky, and why is it not falling to the earth? So remember Newton's laws. The first law was law of inertia, where an object in motion is going to stay in motion. Object at rest stays at rest unless acted upon by an outside force. Second law was force equals mass times acceleration, or acceleration is caused by force, depending on the mass. And then we have action-reaction pairs, which is the third law, where there's a force, there's an equal and opposite force on a separate object. So two objects here versus one object there. And then with that review, let's take a look and let's see if Newton. If the moon followed the first law of motion or inertia, it would just travel straight out of orbit, and it would just keep on going straight ahead. We'd lose our moon and we'd never see it again. And if it acted like an apple and fell to the ground, that would be devastating. I mean, that would destroy a lot of life. There'd be a lot of bad stuff going on. So that doesn't happen either. And he just kept on thinking. He said, well, maybe both is happening. What if inertia is keeping the moon going forward while the Earth is attracting it, and also now you have this satellite path. So you have this orbital that the moon is taking around the Earth. And so that's what's happening, and Newton kind of came up with that idea. And the things that happen on Earth are the same things that happen on in the universe. There's nothing different. We got the same laws. It just happens that on Earth we see a lot of friction. Objects stop because of friction. So we don't see that objects keep on moving a lot of the time. So that gets us to Newton's law of universal gravitation. And in this equation, Fg stands for the force of gravity, and M1, M2 stand for two different masses. It really doesn't matter which one you call them, M1 or M2. And D is going to stand for the distance between the centers of those masses. So there would be your D there. And then it's universal because everything attracts everything else. So you're attracted to your neighbor, to your chair, to your pencil. You're attracted to everything. It's not just the Earth, but the Earth's so massive, it does make a difference. You do feel it. You don't feel the other attractions. If you were going to, so we dealt with Fw equals mg before. That was one of our old equations. So Fw equals mg. Well, with Newton's law of universal gravity, you could go ahead and you can do the same equation, but you could do it in long form. You can go ahead and you can take the Earth's mass. You can take your mass. So looking back at this equation, if you were going to figure out instead of going just Fw, you can solve for the force of gravity on you by taking your mass, the Earth's mass, taking the distance between you, let me just draw you right here, and the center of the Earth. The pen's going weird on me. And the center of the Earth right there. And so that'd be the distance in this equation. And then you can call that mass 1, you can call you mass 2, and then g is always going to be 6.67 times 10 to the negative 11th. Don't confuse it with little g, which was 9.8 times 10 to the, so just 9.8 meters per second squared, or sometimes 10. We use 10 in a lot of our lessons. Okay, and this value never changes, so one time it's not going to be that number, and that is our g. The only time it's going to change is if we're doing the law of ones, which is we're kind of looking at ratios. In that case, it's going to be the same number, which in the law of ones, that would mean that we place a 1 in its place and not that number. And just looking back at the equation, I already mentioned it earlier, mass 1 could be the moon, mass 2 could be the Earth, the distance between the two would be there, and we can plug in all our values and we can figure out what the force of gravity between the Earth and the moon is. Another thing you should know based on this equation, how does force of gravity relate to any one of these masses? And the way to think about this is if you make everything 1, so 1, 1, 1 over 1 squared, Fg is going to be 1. But if you make one of these masses 2, 1, 1, 2 over 1 squared, Well, all of a sudden the force of gravity now becomes 2. So 1 went to 2. This is directly related because if one goes up, the other one goes up. Now, distance is kind of a weird thing, because if you had 1, 1, 1 over 1 squared, FG would be 1. But if you change it to 1, 1, 1 over 2 squared, FG actually becomes 1/4. So it goes from 1 to 1/4, and that's called inverse squared. It's not just inverse, but inverse squared. On a graph, that would look like this. At the beginning, you have a really big, so right at the beginning of the distance apart, you have a much greater change in force. And as it gets farther and farther and farther away, it's going to be less and less apparent as you get to, like, say, this distance over here. But right at the beginning, there's a huge change because of, once again, it's the distance is inversely squared, the distance between the radii of the planets, like you see in this animation. Okay, while you're typing numbers into the calculator, you're going to have a lot of big numbers or small numbers, but either way, they're going to be scientific. 6.67 times 10 to the negative 11th. The way you, and that's not for negative 11. Try that again. Negative 11. In order to type this in, all you would have to do is type in 6.67. So 6.67. At that point in time, you'd see 6.67 up here. And then all you have to do is, there's a thing you're going to try to get, that little EE. You have to hit second, and then you have to hit this button, and that will pull in this, and your calculator is going to say E. And after you type that in, all you have to do is type in 11 afterwards. Sorry, negative 11. Until you just type in 6.67, second EE, negative 11, nothing else. You don't put it like a caret or anything. You don't make an exponent. It's just like that, and your calculator will look like something like this. And this is 6.67 times 10 to the negative 11th in a calculator. Another thing to note, when you're typing in a lot of equations, notice what I did here. You should have extra parentheses around the numerator. That would be the top of the equation. And you should have extra parentheses around the denominator. You'll notice how I have extra parentheses. This is going to be important, because if you have two numbers multiplied on the bottom, your calculator will take the number up top, divide the first number, but then it would place the second number on top. You'll realize you'll make the mistake and you'll change your ways. But come back and look at this and what I'm talking about when you do make that mistake. If not, keep on using your calculator the way you do it. Okay, so let's look at an example, plugging in 6.0 times 10 to the 24th kilograms for the Earth's mass, 7.35 times 10 to the 22nd kilograms for the Moon's mass, and the distance between is 3.844 times 10 to the 8th meters. Go ahead, pause the video, make sure you're using G of this number right here, and then come back and take a look at the answer. Okay, so this is what you typed into your calculator. Once again, extra parentheses around the bottom, and you'll get force of gravity was 1.99 times 10 to the 20th newtons, and this is going to be an attraction. It's always going to be an attraction. Attraction. I think I spelled it right. So attraction to these two planets. Once again, they're going to want to fall together, but the moon, since it's going in, it's going to follow a circular path instead. So it's not falling; it's going forward and falling at the same time. The force of gravity is a really small force. Something just to note, let's just look at this equation right here. This number, which relates all the other parts of the equation together, is 0.0000000000000 10 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 6.67. It's a really small number. So what's going to happen is that it needs large masses to actually feel anything. So like I said, universal gravitation means that you're attracted to everything else. You're going to feel your weight of the Earth pulling you down because it's such a big number. This would have 24 zeros after that decimal place. So you're going to feel your weight, but you're not going to feel your attraction to a neighbor or a table or a chair you're sitting in. So let's go ahead and answer this question. What's the force of gravity between Joe and the Earth? We go ahead and plug it in. Pause it. Once again, if you didn't pause it. Try to type in the number, see what you get. And the answer should be this. Fg equals 938 newtons. And this would just be, if you were going to solve for Joe's weight, if Joe's going to solve for his weight, 96 pound or kilogram Joe on this Earth, it's that size. The G is that. The distance is going to be the radius, because Joe's not very tall versus the Earth's, to the center of the Earth. So you just take the center of the Earth, and that gets you the 938. Now, just take a look. If you're using the force of gravity equation, so you can use 10 or 9.8 down, the negative just stands for down. You plug in the numbers and you get 941. And the only difference between this weight that we solved for the 10 mg versus the big old equation with the big capital G that got us this, the only difference is going to be rounding. If you use the exact numbers, you would get the exact same thing. Okay, here's another question that deals with Newton's third law. How much does the Earth pull Joe down by 960 newtons? Does the Earth pull Joe up by less, more, whatever? And your answer should be exactly the same. Newton's third law says when you have Joe on the Earth, so there's Joe, the Earth is pulling Joe down, but Joe is also pulling the Earth up, and they're going to be equal and opposite. Joe's mass 1, Earth's mass 2, equal and opposite forces. And it's related to the third law. Okay, and then another calculation. Now we're looking at, okay, 96 kilogram Joe and 87 kilogram Jim. The distance between them right here, Joe and Jim, is 0.20 meters. Go ahead and plug it into your calculator and then come back, pause the video, come back and take a look at it. Okay, and this is the answer you'll get. So 1.39 times 10 to the negative fifth. If you're not getting the right answer, double check, make sure you're doing this squared. A lot of people forget the squared. It's not as much of an issue on this type of equation, but it could be. Make sure you have extra parentheses around it. But for the most part, this is a fairly easy one to type into your calculator. It's when you have times 10 to and some other numbers down here. But if you're using EE's, the exponent button instead of just the caret times 10 to, you're going to not make some of the mistakes that students would make by not knowing their calculator. Okay, this is Einstein's idea of universal gravity. What he says, it's kind of like if you think about this is a kind of more of a 2D. They're trying to make it look 3D image. The Earth, if you had like let's say a mattress, you put a big ball on the mattress and you put a small ball next to it. Well, that small ball would be attracted to it, and if there's nothing else going on, that small ball would roll into the big ball. Now the moon is moving forward, so it just ends up following this path. It's going to stay on the very top of it, keeping its inertia going forward, but then falling at the same time, traveling inwards. And if you get really far away, nothing's going to happen. I mean, the little marble down here, you're not going to really feel much of effect. There would be some sort of gravity going on, but it'd be so small, nothing really wouldn't make very big of a difference. But that's Einstein, this guy right here, his idea. Okay, so help rearranging algebra, the equations. So if you're going to solve for mass 1 or mass 2, you'll do this the same way. When you're trying to solve for mass 1 or mass 2, they're in the numerator, so your first step is to multiply out the d squared. So you're going to multiply the d squared there, you multiply the d squared there, and when you multiply the d squared, these are going to cancel out, and you have d squared equals, or d squared fg equals capital G m1 m2. At that point in time, you want to go ahead and we're trying to isolate one of these. So at that point in time, you're going to divide out the G, and you're going to divide out the m2. And once you divide out both those, the G and the m2, and that should have been d squared fg. And take a look. Once you get all that done, these cancel out, and m1 equals, right down here, I just rewrote the fg in front up down here, fg times d squared over capital G times m2, the second mass. And really, really watch out. This is the equation where most mistakes will be made. Extra parentheses, keeping the denominator together. Okay, if you're trying to rearrange this for d, what you're going to do to rearrange this for d, well, first step is the d is on the bottom, so you can't just get rid of G, M1, M2, or else you'll be left with 1 over D. So what you're going to do is you're going to start this the same way. You're going to multiply both sides by D squared. When you do that, you have D squared FG equals G, M1, M2. And at that point in time, now you want to get rid of the FG, and so you're going to divide out the FG. Divide out the FG. Well, when you do that, this pen is spazzing out. When you divide out the FG, now you're left with D squared equals all this. Well, to get rid of that squared, you need to take the square root of it. And when you take the square root of it, there you go. D equals G M1 M2 over FG. So coming back here, if you're having trouble with algebra, come back here. It's a good idea as you get used to the algebra is to rearrange the formula every single time, not try to go back to a memorized version of it or just cheat and go back to the actual version that you can just look at. You always try to rearrange it and come back to this slide and see if you did it correct. Okay, so let's go ahead and solve for distance and mass. If we have distance and mass, we need to we'll go ahead and we'll use those rearranged formulas. And here we have solve for the distance between the Earth, which is this mass, and the Mars, which is this mass, when the force of gravity is that. So go ahead, pause the video, try these out, and then come back and you'll take a look at the answers.
Daddy.
So the first one right here, and it's Halloween today over here, so my son's out there getting candy.
I want my baba.
Okay, here's your baba. Okay, so back to this one. Solving for distance and mass. The distance between the Earth is this, so when you plug all these numbers in, once again, make sure you're plugging it into the correct calculator correctly. That should be 5.1 times 10 to the 15th, not times, that should be 10 to the 15th, just what I had in the PowerPoint, looked weird. Okay, so when you plug in all these numbers, this is the answer you should get. So just double check, and if you're having trouble here, make sure, first of all, make sure you took the square root of the final answer. This is commonly missed. That's a big deal right there. And then secondly, make sure that you have parentheses, especially if you're still using carets and not the EE button, the exponent button. Make sure you have parentheses around the denominator too. So everything should be underneath the square root. You probably forgot the square root if you're not getting the right answer. And this problem right here, the second one, when you're checking your answer, this is where if you don't have extra parentheses around the bottom, your calculator, if you type this in without extra parentheses, you just had this first number times this second number divided by this number times this number. Your calculator is doing all of this first, and then it's taking this number and it's multiplying it by it, that's not what you wanted to do. Your calculator does not see it the way you want it to see it unless by having extra parentheses around the bottom, it's going to help keep these numbers together, and you're going to get this number, the correct answer, the right way most of the time. And then if you take a look, 4.87 times 10 to the 24th, that gets you Venus right here. Okay, law of ones. Law of ones is just a way to figure out ratios. If you hear something like, okay, if I change mass to 5 times more, how is force of gravity going to change? So what's happening to this if I change one of these? And so to do law of ones, you're actually setting up a ratio. And to do that, you want to see, okay, so what's it asking about? It's asking how the force of gravity changes. So you're going to set this up, and it's already rearranged. If I was asked for how the mass or how the distance changes, I would have to rearrange this formula for mass or distance first. But it's asking you for how the force of gravity changes. So this is perfectly fine. And just note the equivalent to FG is that. And we're going to take this equivalent, and we're going to make a ratio. We're going to make everything 1, which means it's exactly the same thing as it was before. Now, this is going to end up being 1 in most equations, but you can use the law of ones for any equation, and often it's not, like there's going to be some equations where this one equal 1. So in order to have a correct ratio every single time, you need to make sure you rewrite the equation down here, the equivalent of the equation of what you're trying to analyze, and then plug in 1s for everything. And so here I say 5, the Earth is, or the force of gravity when the object's 5 times more massive. You're not going to have any changes, or all 1s on the bottom. And it doesn't tell me about anything else. It doesn't tell me about G. Well, G's never going to be anything other than 1. G will never change. That's a universal gravity constant. So these are the problems I was talking about earlier. G's 1 when you do rule of ones. But any other time, G is going to be 6.67 times 10 to the negative 11th. 1 here means it didn't change. It's the same thing as it was before, which is 6.67 times 10 to the negative 11th. So try not to confuse that. This is telling me that my mass is 5 times more. The first mass is 5 times more. This is telling me the second mass is the same thing, or 1 times what it was. This is telling me the distance is 1 times what it was. And when you do the math and you go through all of this, you're going to get 5 times. So that's how you do the law of ones. And if they gave you a force in the first place, like if they say the force was 200 newtons and then you did this, you made the one mass 5 times more massive, well, you just take that 5 and multiply it by whatever the original value. That's what the times means. Okay, here's another one. If you double the distance between the masses, so expect a bigger deal to happen. You double the distance, you do the same thing. 1 over 2 squared, you get 1/4. And once again, this is inverse squared. So doubling something actually has a much greater change at the very end when you think about the ratios in law of ones. Once again, the ratios of only the distance changing to everything being the same. That's why we do the equivalent over the equivalent. Take a second, look at this problem set, pause it, see how you do, and then come back to this video. Once you come back to this video, you'll check the answers, and that's just about it. Okay, so in the first one, what happened to force of gravity? You tripled the distance between the objects. I'm leaving out the 1 over 1 squared. I should always have that, but I was being lazy here. This right here ends up being 1/9. So that's, if you triple the distance, you get 1/9 the original force. Next one, what would happen to the force of gravity if you double the mass of one object? So 1, 2, 1, once again, 1, 1, 1 over 1 squared. This should be squared. I shouldn't leave that off. And that would give you a ratio of 2 times more force. And then the third problem, 1, 2, 1, once again, you should always try not to be lazy, even though it's very easy to when so many of these equations end up being 1 anyways on the bottom. But 1, 2, 1 over 2 squared. So I'm doubling one mass and I'm doubling the distance. So I have a 2 there and I have a 2 there. And 1, 2, 1 over 2 squared ends up being 2 over 4, or 1/2 the original force. And so if you knew the original force, you just multiply it by 0.5 or 1/2.